student, in this video I am going to continue from the last point that was discussing about the audio compression technique, starting with the audio compression technique. So basically in every compression scheme has three stages. First stage is that our input data is transformed to a new representation that is easier or more efficient to compress. So actual analog signal of audio need to be transformed to a proper data, or you can say proper input data, by doing some representations, by doing some new presentations which will be easier to compress or which will be more efficient to compress. We may introduce loss of information here. Due to this compression technique or due to compression, we might face information loss. Actually, that quantization process is the main lossy step. In a third step, that is coding. Coding is that assign a code word, thus forming a binary bit string to each output level or symbol. So for every amplitude, we need to put a binary code word. We need to assign a code word to each output level or symbol. So these are the three steps. First, we need to transform the input data to a proper representations which will be easier or more efficient to compress. That is the transformation step. Second point is that we are going for quantization, which is a lossy step. We will introduce a loss of information. Third is coding phase, where we'll try to put some code word for every specific levels of output or symbol. Some techniques for sound compressions are like PCM, or you can say pulse code modulation, DPCM, where sense differences between samples, ADPCM, which is adaptive or advanced DPCM, sense differences but adapt how we code them, LPC, which is linear model of speech formation, CELP, which also use LPC as base but also some needs to code corrections for the things LPC gets wrong. So these are just terms. We'll try to understand them one by one in brief. So first, the techniques that code received sound signals. How we receive the sound signals using some code that can be done using PCM, pulse code modulation, or DPCM or ADPCM. And there is another two, LPC or CELP. Both are parameterized sound model, which is actually parameterized means model based on coding. LPC or CELP, these two one are parameterized sound model. In case of pulse code modulation, we apply mu law and A law. PCM have already reduced the data sent. However, each sample is still independently encoded. So we'll try to understand mu law and A law in next video. But before that, try to go through this pulse code modulation. Mu law and A law, PCM have already reduced the data sent. So using that technique of mu law and A law, we can already reduce the actual data. However, each sample is still independently encoded. But in case of PCM using mu law or A law, each sample is still independently encoded. In reality, samples are correlated. So in reality, samples are correlated. Can utilize these correlations to reduce the data sent. So we can use this correlation value to reduce the data sent. So here in this figure, you can see input analog speech signal will be given to a band limiting filter. Then apply mu law and A law to compress the signal. Then use linear PCM, pulse code modulation. Then transmit that thing through digital to analog converter Then again mu1 LO for expander. This is expander, but this is compressor. Again going through low pass filter, which will create output analog speech signal. This is PCM signal encoding and decoding. Digital representation of an analog signal. Sampling and quantization we already know. This is the digital signal, or this is the analog signal. We try to sample them, then we try to code them according to the levels of amplitude, decoded strict staircases signals, reconstructed signal after low pass filtering. So this is initial encoding phase. So this is a decoding phase where we can create the original signal. So in this scenario we can see that's the basic operation of sampling and quantization of this signal that is done through this. We have already discussed this type of process in the previous video. In case of this is simple the PCM process or pulse code modulation process, simple the coding process where we try to represent it in digital form, and the process of quantization is actually reducing the information. In case of DPCM, makes a simple prediction of the next sample. So in case of DPCM or differential PCM, makes a simple prediction of the next sample based on weighted previous and sample. So the calculation of next sample is done based on the past values of and samples. Normally the difference between sample is relatively small and can be coded with less than 8 bits. So what is the study here? Study is that the difference between samples is relatively small and can be coded or encoded using 8 bits or less than 8 bits. Typically use 6 bits for difference rather than 8 bits for absolute value. Compression is lossy as not all differences can be coded. Here you can see compression is lossy because all the differences cannot be coded using, or might be fractional also. Difference can be fractional also, but we can only code the digital values only, or we can directly code a specific values of integers only, we can go for fractions. So in that way also we might lose some information. So and next is ADPCM, that is adaptive DPCM or adaptive differential pulse code modulation. Different coding techniques in comparison with DPCM. So here the coding techniques are same for all samples, but in case of adaptive DPCM, the coding techniques might be different for different samples. Two methods. One is adaptive quantization, means we can quantize the sample adaptively, or quantization levels are adaptive based on the content of the audio. And also second method is adaptive prediction, means here in the differential PCM we try to predict the next sample by having the knowledge of the previous samples. So here also the prediction is enhanced by creating some adaptive rule. So receiver runs same prediction algorithm and adaptive quantization level to reconstruct the actual speech. That is the idea of adaptive DPCM. In the next one, that is model based coding. In case of model based coding, PCM, DPCM or ADPCM directly code the received audio signal. An alternative approach is to build a parameterized model of the sound source, that is human voice. So an alternative approach is to build a parameterized model of the sound source. For each time slice, suppose 20 milliseconds, analyze the audio signal to determine how the signal was produced. Determine the model parameters that fit. So first, analyze the audio signal to determine how the signal was produced. Second, determine the model parameters that fit. Third, send the model parameters. So this is the step for model based coding, because we need to build a parameterized model of the sound source. At the receiver, synthesize the voice from the model and receive the parameter. So using some synthesizer, the voice from the model will be created and by using the receive parameters. Speech formation, how we can create the speech. Voice sounds series of pulses of air as larynx opens and closes. Basic tone then shaped by sensing resonance of vocal tract. Unvoiced sound, larynx held open. Turbulent noise made in mouth. That is unvoiced sound. One is voiced sound when the larynx opens and closes by creating some pressure in the air or series of pulses of air when larynx opens and closes, and due to that basic tones can be shaped or then shaped by sensing resonance of vocal tract. But in case of unvoiced sound, larynx held open, turbulent noise made in the mouth. LPC is a linear model introduced in 1960, low bit rate encoder, we can say 1.2 kilobyte per second or 4 kilobyte per second. Sound very synthetic. Basic LPC mostly used where bit rate really matters. Means example in military applications where bit rate means number of beats should be higher, number of beats of sound should be higher. In that scenario, LPC is used. Most modern voice codes, example GSM, are based on enhanced LPC encoders. In case of LPC, we try to digitize the signal and split into segments. For example, suppose 20 milliseconds. For each segment, we need to determine this type of information. First, pitch of the signal, which is the basic format frequency, loudness of the signal, and whether the sound is voiced or unvoiced. Voiced is like the vowels M, V, L. Unvoiced is F, S. Vocal tract excitation parameters. Another parameter is that vocal tract excitation parameters, LPC coefficients. Those things need to be determined for each segment of the digitized signal to create the linear model. But there are limitations of LPC model. LPC linear predictor is very simple. For this to work, the vocal tract tube must not have any side branches. This would require more complex model. If the vocal tract or tube have the more number of branches, side branches, then the model need to be more complex. And LPC is okay for vowels only. Tube is reasonable model. For nasal sounds, nose activity forms a side branch. So if your voice have some nasal sounds, the nose cavity forms a side branch, then it will create some problem. In practice, this is ignored in pure LPC. In more complex codecs, attempts to code the residue signal which help correct this, so we can rectify the problems. So I'll try to conclude today's video. I'll continue with more about the different types of compression techniques of audio or sound, digital sound. These topics just I try to give some hints only, and the basic ideas or basic terminologies. To go deep in these parts, we need to go for more about signal processing and all, which will be out of scope of the syllabus. So I am not going too much deep, just giving you the hint and name for better understanding, and to just have the knowledge about the names and terminology as well, and just basic concepts of compression techniques. So try to go through these techniques and names and terminologies through the book also. If you have any problem, please let me know, or if you want to add anything more than this, please let me know. We'll try to resolve or discuss over Google Meet. Thank you.